Hello everyone, I welcome you all for this session, that is LPC 2148 peripherals in unit number 6. In that session 4, that is phase locked loop. In the last session we have discussed about the pin connect block and its features and its resistors, and in that even we have studied the GPIO features and its resistors and some of the assessment questions on PCB, that is pin connect block, and GPIO. In this session we are going to learn what is meant by this PLL and the PLL features and its block diagram and some of the resistors used in PLL and some of the assessment questions related to this PLL. And you can see the block diagram of ARM controller, that is ARM7 TDMI. See, in this block diagram you can see the PLL0 and PLL1. So there are two PLLs in ARM7 TDMI. Structurally both are identical, but here the PLL0 is used to generate the system clock, okay, and PLL1 is used to generate USB clock at the rate of 48 MHz, and the system clock ranges from 10 to 60 MHz. So here the external clock frequency is supplied through this Xtal1 and taken out from this Xtal2 to make the loop, and these two PLLs are used to generate the stable frequency or the stable clock signal for system chip operations as well as the USB separately. Okay, so and as we know, there are two PLLs, PLL0, there are two modules, as you can see here, two PLL modules, that's nothing but PLL0 and PLL1. This PLL0, as I said, PLL0 is used to generate the CCLK, that is system clock or CPU clock for internal chip operations, and PLL1 is reserved to generate the clock signal for USB, and that is at the rate of 48 MHz. And this system clock ranges from 10 to 60 MHz, and usually this PLL is used to generate the stable frequency. Okay, so and these are the features of PLL. Here the PLL accepts the clock frequency in the range of 10 to 25 MHz through Xtal1, and this input clock frequency is multiplied. That's very important because our CCO is in the range of 10 to 60 MHz, and this USB clock is at the rate of 48 MHz. So in order to get the frequency from 10 to 25 MHz to 10 to 60 MHz and the USB clock 48 MHz, so we need to multiply up to the this range, that is 10 MHz to 60 MHz. And this PLL, the main body of the PLL uses current controlled oscillator. So in order to translate the input frequency to this range, and here we have two parameters. So in order to perform this shift in frequency, that is multiplier and the divider value. This multiplier we call it as M, and the divider we call it as a P, and the values for this multiplier ranges from 1 to 32, but as you can see the input clock frequency, that is 10 MHz to 25 MHz. If the input is 10 MHz, what you can get, the maximum 60 MHz. So it means practically this multiplier value cannot be more than 6, and the current controlled oscillator operating in this range 156 MHz to 320 MHz. So there is an additional divider is required, that's a P value. So in order to keep this CCO within its frequency range, because our output CCLK or the CPU clock is in the range of 10 to 60 MHz, but our PLL is using the CCO in this range. So additional divider is used in order to keep the CCO in its operating range, that is 156 MHz to 320 MHz. The output divider may be set to 248 or 16 to provide the output clock. So it means 156 MHz to 320 MHz CCO frequency can be divided with this value, so in order to keep the frequency in its range. Okay, so as you can see, the block diagram of this PLL contains these components. Looks like very complicated one, but you need to understand the different components. See, these two, this FOSC, this is oscillator frequency. You can get this frequency through external one, and this CCLK, that is CPU clock. So it means, so here we have drawn the PLL 0 block diagram, but anyhow the PLL 0 and PLL 1 have structurally both are identical. Instead of CCLK you can put that is USB clock, so that is 48 megahertz. Now here this is the input clock oscillator frequency, and this is the CPU clock, that is system clock, and this M and the P are the parameters, that is P is the divider, M is the multiplier. This is CCO, current controlled oscillator. So this phase detector, so it will see the output clock signal frequency and the input oscillator frequency signal phase difference. So phase difference means if you have two waveforms like this, so if your output frequency is also started at the same frequency, then we say that there is no phase difference. Then it means what? We have maintained the constant frequency of the output signal. If there is any drift, so it means if any change in the phase, so this is the phase difference, and what you can call it as pi. So if there is a phase difference between the loop signal, that is feedback signal, and the oscillator signal, then the error signal will be generated. Based upon that error signal, the CCO will change the frequency of this CCLK in order to maintain the constant or the stable signal frequency. Here you can see the two bits, that is PLL enable, so PLL connect. So these two bits are available in PLL con resistor, that is PLL control resistor. So practically these two bits must be high, so in order to use this PLL completely. So, and these M cell bits, that is multiplier select bits from 0 to 4, that is 5 bits, and this P cell bits, that is divider value select bits from 0 to 1, 2 bits. Here 5 bits and here 2 bits. These bits are nothing but configuration bits, PLL configuration bits. These are available in PLL configuration register, and these are nothing but 2:1 multiplexer. So in order to select whether the PLL frequency or the direct frequency, you can see here if both are 1 here, means PLL is enabled and it is connected. Okay, so then the output is 0. So it means 0 in the sense what? Here this channel will be enabled. So CCLK is connected to the output of this PLL block diagram. Suppose if it is not connected, then this channel will be enabled. So directly oscillator frequency is supplied to the CPU or the system. So there may be the variation in this oscillator frequency due to so many conditions, but in order to maintain the stable frequency, this CCLK must be the must take the input from this PLL. Okay, and here you can see the bypass 0, that is bypass. Here directly with FOSC can be directly connected to this if this bypass is applied. Similarly, if you do not want to divide this CCO, then you can use bypass. Here also there is a direct signal, so it means directly the output of this CCO can be directly fed into the CCLK. So this is the overall block diagram of PLL, but ultimately we need to understand the PLL is used to maintain the constant frequency. And here the due by M, it looks like it's a complicated one and confusing. So actually this is the multiplication to the CCLK, because CCLK formula, you know, CCLK equal to M into FOSC. So here this is the divider for CCLK, so definitely it's a multiplier for FOSC. It's a feedback loop, so it must be divided by this CCLK, then the for this FOSC it becomes multiplication. Okay, so in this slide, we're going to learn what are the resistors available in PLL. There are four resistors. PLL con resistor. As I said already in the last slide, the PLL con resistor contains a PLL connect C and PLL E bit. In this resistor, you have two important connect and E bits. And PLL configuration resistor contains multiplier and P, that is division values. Okay. Then PLL stat resistor contains the PLL parameters, nothing but the C, E, and multiplier value is M. Then divider value is P, that is P cell bits, M cell bits. Okay. Then PLL connect bit, then PLL NM. So all these information along with P lock, there is one bit, it's an 16-bit resistor, status bit resistor P lock. This lock signal is also available in this PLL stat resistor. Here this status resistor is just a read back resistor. So in order to understand the configuration bits and the control bits of the PLL operation. Then one important resistor, that is PLL feed resistor. So this resistor is used to activate the configuration and control values. So here the PLL feed resistor is a 8-bit resistor, and it should contain the value AA, and the complemented value of AA is 55. That it looks like a one clock pulse. So initially it is 1, then zeros like this. So alternate bits are high and low. So this PLL feed resistor is loaded with AA and 55. Then these PLL con and PLL CFG configuration and control resistor bits become active. Okay, so we will see some of the questions on this. How many PLL models are there in LPC215? It's very easy. So how many are there? PLL 0 and PLL 1. So the answer is 2. Next, system clock, that is CCLK, and you can call it as CPU clock also. It is generated by, that is PLL 0, because we have reserved PLL 1 for USB clock. See here, this is a PLL 0. And similarly, as I said, USB clock, that is at the rate of 48 MHz, is generated by PLL 1. PLL accepts the input clock frequency in the range of 10 to 25 MHz. Okay. Then the frequency range of CCO, it's the heart of your PLL, current controlled oscillator. The CCO gets the input from the phase detector. So depending upon the phase difference, okay, CCO operates in the range of 156 MHz to 320 MHz. But our CCLK or the CPU clock is in the range of 10 to 60 MHz. So in order to keep the CCO in this operating range, we will have to divide this using P. So CCO range is 156 MHz to 320. Thank you one and all.